This is free response question 6 from the 2024 AP Calc AB exam. It's part of the No Calculator section. The functions f and g are defined by f of x equals x squared plus 2 and g of x equals x squared minus 2x as shown in the graph. So there's f of x, that's x squared plus 2, and there is g of x, that's x squared minus 2x. Part A says, let R be the region bounded by the graphs of f and g from x equals 0 to x equals 2, as shown in the graph there. Write, but do not evaluate, an integral expression that gives the area of region R. So this is just the area between two curves. From the graph, we can see that the upper function of this region, the upper bound, is f of x, and the lower bound on the region is g of x. So for part A, the area of the region R is going to be the integral from x equals 0 to x equals 2, and then we just need the area under this curve minus the area under this curve. That's going to give us this total area between them. So we're going to integrate from 0 to 2, f of x minus g of x. We could replace f of x and g of x with what they actually equal if we like, but it's also fine to leave the answer like that. On to part B. Let S be the region bounded by the graph of g and the x-axis from x equals 2 to x equals 5, as shown in the graph. That's this region here between g and the x-axis. Region S is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis is a rectangle with height equal to half its base in region S. We want to find the volume of the solid and show the work that leads to our answer. So the base of the solid, like it says, is this region S. And the way the solid is made is that its cross-sections perpendicular to the x-axis, so going this way, perpendicular to the x-axis, these cross-sections are rectangles, something like this. The base of the rectangle, of course, lies in the region S, and so the length of a base at a given x value would just be the corresponding y value. That would be the length of the base. The height, on the other hand, as the question says, is 1/2 of the base. So this drawing is not quite to scale, but that's how it works. Here's the base, and the height of a rectangle at any cross-section will be half the base. If I redraw the sketch a little bit more to scale, it might look like that. So this is coming out of the base S, coming out at us. This region is going from x equals 2 to x equals 5. So to find the volume of this solid, we will need to integrate from x equals 2 to x equals 5, and all we have to do is add up all of those cross-sectional areas. The area of each cross-section is just the area of the rectangles. Now, for any given x value, the base length of the rectangle, like we said, is just the corresponding y value. It's like the height of the function. And y is g of x, which is x squared minus 2x. Let's just write it as g of x for now. So that's the base length of a rectangle. And then the height of the rectangle, right? We need to multiply by the height because base times height gives us the area. The height, we were told, is just half of the base. So if the base is g of x, then the height is 1/2 g of x. So this is what we are integrating from 2 to 5. Then we can take this half out of the integral, and g of x times g of x, of course, is g of x squared. At this point, we can recognize that g of x is x squared minus 2x, and so we just have to square that, which would give us x to the 4 minus 4x cubed plus 4x squared. That's just doing x squared minus 2x times x squared minus 2x and distributing. That gets us here. Now, integrating this is straightforward. We just have to use the power rule. And it leads to this long line of calculations. X to the 4 integrates to 1/5 x to the 5, minus 4x cubed integrates to minus x to the 4, and 4x squared integrates to 4/3 x cubed. You could try taking the derivative of any of these terms and find that it gets us back to the corresponding term in the integrand. We then plug in the upper bound of 5 and subtract, plugging in the lower bound of 2. Then everything from there is just some arithmetic, And at this step, we distribute the 1/2, so the 500 becomes 250, 32 becomes 16, and so on. And then we're just left with combining the fractions, so we get a common denominator of 15, then reduce that fraction. Final answer is 414/5. Finally, finishing with part C. Write, but do not evaluate, an integral expression that gives the volume of the solid generated when region S, as described in part B, the region we were just talking about, is rotated about the horizontal line y equals 20. So let's come up to the graph and think about what this solid of revolution looks like. This says the region S is rotated about the horizontal line y equals 20. The horizontal line y equals 20 is right about there, and so we're taking this region S and revolving it about that horizontal axis. So we can sketch a reflection of this region, which would look something like this, and then the circular cross-sections of the resulting solid would be washers. They'd have exteriors traced out by the x-axis revolving about the horizontal line. But then the interior would be cut out by this guy revolving about the horizontal line. So we would have a circular cross-section that looks something like this. Again, the outer part of the washer is traced out by the x-axis revolving about the horizontal line, but then the inner part is carved out by this curve revolving about the horizontal line at y equals 20. So the area of each cross-section is going to be the area of the big circle, traced by the x-axis, minus the area of the small circle, cut out by g of x. This integral will again go from 2 to 5, and what we're basically going to have is pi multiplied by the big radius squared, that's the area of the big circles, minus pi times the radius of the small circles squared. So I'll use little r for that. These are going to be in terms of x, so this would be dx. Coming up to the sketch to figure out what these radii would be, the radius of the big circle would look like this, just the distance between y equals 20 and the x-axis, which is always just 20. So the big radius, that's 20. Now what about the little radius? Well, that would look like this. It's the distance between y equals 20 and g of x. So that little radius, r, is just going to be 20 minus g of x. So then for our integral, we can take the pi out of the integral. So that's going to be pi multiplied by the integral from 2 to 5, and then we just have the difference of the radii squared. The big radius is 20 squared, and then we subtract the small radius squared. The small radius is 20 minus g of x, and this small radius needs to be squared, and that's it. This is an integral with respect to x. And we're in luck because we do not have to evaluate that, so that is the answer. And that completes our solution to free response question 6 from the 2024 AP Calc AB exam. Let me know in the comments if you have any questions, and be sure to check out my Calculus 1 course and Calculus 1 exercises playlists in the description for more. For a little bit more practice, check out my 10 hours of AP Calc FRQs linked in the description as well. And that completes our solutions to the free response section of the 2024 AP Calc AB exam. Let me know in the comments if you have any questions, and if you're looking for the BC questions, there will be a link in the description to my solutions for those. Be sure to check out my Calculus 1 course and Calculus 1 playlists, also linked in the description, and my 10 hours of AP Calc FRQs video if you're looking for a little bit more practice, in the description as well. Thanks for watching.
I'm the mathematical menace, the machinations of mankind, two calculators at the same time, hand signs and abacus, finger count and calculus. I'm the V to the T, my parameter the rapidest. Happens like this, my lectures the most prominent, dominant. Call me the Morgan, I get the compliments. The union in together like any time that we intersect, cause my opponents know they need